what we're going to do, okay, if I only have one basis vector, what's the only possible way I can differentiate different signals? So in other words, I just have a number line, or I just have a vector like this. So everything has to be collinear with that vector. What's the only thing that I can do?
The size, the amplitude, like 1, 2, 3, 4.
Exactly. So basically what I have to do is I have to scale this one vector by different amounts. So this is exactly what we've seen before. So each signal, I should mention, I'm going to use the following notation. So remember, my symbols were labeled 0, 1, and so on up to m-1. So whereas before, in binary, I had S0k and S1 of k, now I'm going to have, these were the modulation functions for each bit. Now the modulation functions for each symbol, S0k, S1 of k, and so on up to Sm-1 of k. So in other words, when I pick one of these symbols, I'm going to replace it with the corresponding function. And what I'm going to say is that Si of k is equal to this fundamental basis signal S of k times alpha I. So in other words, I'm going to pick coefficients alpha I, all different, that will scale that fundamental basis, that basis vector. Okay, furthermore, I am going to assume that this fundamental basis vector S of k is normalized. In other words, the norm of S of k is 1. One more assumption, without loss of generality. What I'm going to do is I'm going to assume that alpha I are arranged in decreasing order. So alpha 0, greater than alpha 1, greater than alpha 2, and so on. And this is the same assumption that I made in binary. I always assumed that the assumption I made was if you think about BPSK and polar NRZ, in that case I always had the coefficient multiplying S0, so this would be equivalent to S0. The coefficient multiplying by S0 is -1, and in on-off keying, it was 0. So this is just a generalization of what we've seen up to this point. Okay. As I mentioned moments ago, this is a one-dimensional vector space. So in order to pick out the coefficient that is attached to each, in order to pick out these coefficients that are attached to each signal, I should only need one matched filter, so that's what I'm going to use. So use a matched filter. me. I'm not going to go quite to the match filter yet. What I'm going to do is I'm just going to use a detection filter. Call this H of K. So what I'm going to do in the noise-free case, so remember my procedure for analyzing probability of error. What I first need to know is what are the noise-free means. So before I had 2, and now I have M of them. Noise-free means, in other words, if I pass signal S of I, Si of K into the detection filter, what do I get on the other side if there's no noise? So Sik involved with H of K. This is equal to, let's call this Si. That's what I used before. I used S0 and S1. And this is evaluated at time NB. Okay, I know that Si is equal to alpha I S of K, involved with H of K, evaluated at time NB. And since this is just a scalar, I can take that out of the convolution. And I just end up with alpha I times this quantity. So let's let H be equal to Sk involved with Hk. So that's nice. Up to a constant, up to multiplication by a constant, actually doesn't matter what filter I use, I'm going to pull off this coefficient AI. So hopefully I'm not stupid enough to choose my detection filter orthogonal to my signal. If I did that, it would just wipe this out, it would be 0. So basically up to this multiplicative constant, I'm going to get out of the match filter with this coefficient. So ultimately, what's going to happen is that this H is going to be the match filter for S, but I want to show that later, so I want to keep this general for now. So my noise-free means are Si, where Si is equal to alpha I times H. The next thing I need is my variance. That is actually no different. So if I just have the one filter, the one detection filter, remember the variance is only concerned with what the filter is. I have a general filter, H of K, so the variance is no different. So this we can look back in the notes and do the same thing that we did back when we were talking about straightforward detection. I'm just going to leave this as a symbol, sigma squared. It's exactly the same as what we did before. The variance has nothing to do with the signal. It just has to do with the filter. Okay, now it gets a little different. Threshold. So, in order to design our system and calculate the probability of making an error, I need to know where I'm making my decisions.